Alright, welcome to the final homework solutions for thermodynamics 2 at the South Dakota School of Mines and Technology. Homework number 8 is on reaction equilibrium. Problem number 7 is an adaptation of Kretzky 9.21. Okay. It says 9.21. So basically it says using the data from Kretzky 9.21, answer the following questions. At the same temperature, pressure, and feed ratio, how much sulfur trioxide is made if you feed in 1 mole of sulfur dioxide? Okay. At the conditions stated. Okay. That's not an H, that's a plus. Okay, so I have sulfur dioxide, I add some oxygen from air. So what does that mean? That means I also have nitrogen as an inert. Okay, so I have nitrogen, oxygen, sulfur dioxide, goes sulfur trioxide, and then of course I have nitrogen again because it's technically inert. Okay, it's saying at the same temperature and pressure, wherever it is, the feed ratio, whatever it is, how much trioxide is made if you feed in 1 mole of sulfur dioxide. So I'm basically asking what's the extent of reaction. Okay, now I'm going to set this problem up in Excel. I don't have Excel to show you, so I'm going to, but I would set this up in Excel, so I just have to change a couple little things. So I'm just going to go through the equations that I want to see on the piece of paper. I'll let you set up the Excel, okay? But what do? First, I balance the reaction. 1 sulfur, 2 oxygens, 3 oxygens. Whoops! Okay, well, 4 oxygens, 3 oxygens. Okay, so I need 4 over here. Yeah, 4 oxygens, 3 oxygens. So I need 2 over here. 2. What's there? 2, 6, 6. Okay, so 2 sulfur dioxides plus 1 oxygen goes to 2 sulfur trioxides. Okay, so now I'm balanced. And now I do my table. Okay, so I'll call the species 1, the species 2, the species 3, and I'll call nitrogen species 4. So species. Now why do I care about nitrogen? Well, because it's going to affect my totals. So species 1, 2, 3, 4 total. Then Ni naught plus nu I times squiggly equals Ni. Okay. How much do I have initially as sulfur dioxide? Well, that's when I have to read the problem. It says, considering, okay, 1 bar, 100% mole percent excess of oxygen, so I have twice as much oxygen as I have sulfur dioxide. Actually, well, not even, I have even more than that. I actually have equimolar. Because if I have 2 moles of sulfur dioxide, I only need 1 mole of oxygen, so it says I have 100% excess, so whatever I have as sulfur dioxide, I have of oxygen. Okay. And it doesn't say how much I begin with, so I'm going to assume a basis of 2. Okay. Just to make things easier. Okay. Or actually, let's do it as a basis of 1. Again, to make things easier. Okay, so I have 1 of those, I have 1 of those, I got nothing of component 3. How much of nitrogen do I have? Well, if I have 1 mole of oxygen, oxygen is 21% of air. So I kind of have to figure out the math to figure out how many moles of nitrogen there are. Well, 1 is equal to 21%. So 21.21, wait a second. Yeah, I gotta figure out the math. So I think I have, I should have approximately like 3, we'll say. We'll just say 3 for argument's sake. I don't know what the number is. You'll have to figure out the math. Oh, wait. Well, 2.5. 2.5. Okay. But whatever it would be. Okay? Alright. Okay, plus nu I. Okay, well this one is minus 2 squiggly. This one is minus 1 squiggly. This one is plus 2 squiggly. And this one is obviously plus 0 squiggly. So when I'm all said and done, I have 1 minus 2 squiggly, I have 1 minus squiggly, and I have, here I have 2 squiggly, and here I have just 2.5 or whatever it is, which makes sense. Okay, I add them all together, I get about 4.5 or whatever it should be. My thing of reaction is going to equal minus 1 squiggly, so I have 4.5 or whatever it is minus squiggly. Okay. And I know that's hard to see, but I'm running out of resources here. Alright. And then I get my K. Okay, I set up all that math in Excel. Okay. Not that hard. We did it in class, or we should do it in class. But now I have this in there, but that doesn't really change much. You know, I still have 0 here. All the math should work out, because even when I do my K formula, K again is equal to pi times fugacity over fugacity naught to the nu I. Well, the nu I of that one is 0, and anything to the 0 is 1, so it's not going to affect anything. So when I'm all said and done, I should have, because everything's a gas, n4 squared over n1 squared times n2 times, my nu in this case is minus 1, so I have n total over pressure. But again, I don't even need that because I'm going to have yi in my Excel, and it's going to figure everything out for me. I don't need to worry about anything. Okay. But I'm just having that so I can kind of do the qualitative questions on the next part. And again, in terms of getting K, the same formulas again, and I'm just going to write them for reference sake, but I'm not going to get them. So, you know, I got K naught, which is equal to exponential of minus delta G naught of reaction over RT naught. I've got natural log of K over K naught equals minus delta H naught of reaction over R times 1 over T minus 1 over T naught. And then I got delta G naught of reaction is equal to summation of nu I times delta G of formation of component I of naught, and delta H naught of reaction equals summation of nu I delta H I formation of naught. I mean, and then I just plug and chug again those things into Excel. I don't need to do anything fancy. Well, I lost my thing. Okay. I don't know what I was asking for because I lost my, but I can guess because I wrote the problem, so I'm sure. My computer died, so I don't know what the question's asking, but I can guess what I want to know. I know the first thing was like, what's the conversion? Okay, here's the conversion. Okay, well I just solve for squiggly. Okay. I mean, after this point, I have everything set up. I just need to solve for what squiggly is equal to. I'm sure one of them asks, okay, I want to do something with the temperature. And so really, I just need to see, what do I want to do with the temperature? Well, it depends. Is this exothermic or endothermic? Okay, so I look up my heat of formations really quick. And so I got sulfur dioxide and sulfur trioxide, right? Okay. So trioxide is negative 395, dioxide is negative 296. So this is easily exothermic, okay? So this is exothermic. Okay, so it's releasing heat, okay? So I want more products, okay? What do? Well, I lower the temperature, okay? But it could be asking, okay, the temperature's too high. How do I lower the, what do I need to do to lower the temperature? Okay, let's say the temperature is too high, I need to lower the temperature. It's exothermic, okay? It's exothermic, so if I lower the temperature, that's a good thing. I should get more products anyways, okay? Because if I lower the temperature, the K will go up, and my products will go up. Okay. If I want more products, well then I just lower the temperature, and that's also a good thing. All right. Let's see here. Pressure is another one I probably would ask about. Okay, maybe the pressure's too high. Okay, because that's usually a bad thing. Is pressure's too high. So the pressure's too high. Could be that it's too low, but it's too high in this case. So what do I want pressure to do to maintain the same extent of reaction? All right. Well, pressure goes over there. K goes over there. Pressure goes down. K stays constant. So that means my extent of reaction is going to go down. So I don't want to lower the pressure. Why? Because nu is less than 1. Okay. Sorry, less than 0. So if I lower the pressure, I'm lowering the amount of products. So I want to keep the pressure high if I can. Okay. Otherwise, I'm going to have to change some other condition to keep the pressure low. So maybe I decrease the temperature so I can have the same extent of reaction, which will decrease my pressure. Why? Because the lower temperature is going to increase this, and an increase of this is going to make a decrease in pressure. Okay. The final one is probably, okay, I want to remove that nitrogen. Should I remove that nitrogen? I mean, is it worthwhile in this case? Well, let's think about that. If I lower the nitrogen, that means I'm lowering the total moles. And if I lower the total moles, okay, well, that goes down. That means the products have to go up. Hey, that might not be a bad choice. Now, economically, it might not be feasible to remove that nitrogen. You know, let's face it, pure oxygen is expensive for a reason. Okay, but you know, it might be worth it to. I mean, it depends upon how much that product's worth. Okay, and so on and so forth. So, you know, from a senior design point of view, a reactor design point of view, I need to look at both scenarios, okay? One where I have nitrogen, but I have a lower conversion, and one where I don't have nitrogen, but I have a higher conversion. Which one's more economically feasible? But this isn't economics, this is just thermodynamics. The thermodynamics say, remove that nitrogen, get it out of there.